Good day. In this video we will talk about Newton's third law. When you push on something, let's say you push on the wall with your hand, right? That's your hand. As you push your wall, as you push your hand deforms slightly. The skin in your hand deforms slightly, gets flatter. The harder you push, the flatter your hand becomes. So as you push with a force, hand on wall, the wall pushes back on your hand with a force, wall on hand, right? What we notice is that the force, wall on hand, is equal to the opposite of the force, wall on hand. And we call this the action, and we call this the reaction. So something remarkable appears now. Forces are nothing but the interaction between two bodies. Two bodies. In this case, the hand and the wall. It's impossible to have forces living alone in the universe. Every time one force exists, a reaction needs to happen. And that reaction will have the same magnitude, but opposite direction, and it is also going to be of the same nature. If this is your pushing, well, the other one is also going to be a push. If one is gravitational, the other one will be gravitational. If the action is electric, the reaction is also going to be an electric or force. In more general terms, the force that object A exerts on object B is equal to the negative of the force that object B exerts on object A. Let me show you one thing. Imagine you have a book on top of a frictionless surface. Let's say it's ice. So you push with 100 newtons, and then of course there's going to be a reaction with also 100 newtons. So then we say we have 100 newtons to the right in the I direction plus 100 newtons to the left in the negative I direction, so negative here. That gives us 0. So how come when you push this block is going to move? What gives? I push with 100, then the reaction is 100. They should cancel out and there should be no motion. Well, this is a very common mistake when dealing with the action-reaction, when action and reactions. And this is fundamentally wrong. The setup of the question is wrong, because the action and reaction, these are forces that act on different bodies. So my drawing is wrong. What you have to say is you push on the block, on the book, with 100 newtons, and then a different body diagram is your hand being pushed by 100 newtons. So when you analyze the book alone, you only show the force acting on the book. On a free body diagram, we don't put the forces exerted by the body. So similarly, if this is the earth and this is you, this is a system. You have two bodies. If you consider the two bodies together, then whatever force, the gravity of Earth exerts on you is going to be the opposite of whatever force you exert on the Earth. But you see, if you treat the Earth and yourself as part of the same system, these forces are internal and cancel out, right? that will happen. The action and reaction are internal to this system, and then they don't show up in the system, because on free body diagrams we only put whatever is external to the body. But here you have a common body, which is you and the earth. So what you have to do is draw the free body diagram of the person, where you put the weight, right, mg, as we saw in the other video, and then you do the free body diagram of the earth, which feels a force equal to same mg. You don't put the mass of the earth here, is the mass of this person. Remember that this comes from the g, m, and r square. So the g, this g also already considers the earth. So you see, this is the reaction, this is the reaction. Now let's do a little bit more complex scenario that involves this as well. Once again, I'm going to put the earth, that's the earth. I'm going to put a table, and then I'm going to put a book or a box. Okay, so this is the table. So let's find out, let's draw the free body diagram of the box. So this is the free body diagram of the box. And what we have is going to be gravity acting down, which is going to be mass of the box times g. And then we're going to have another force, which is the contact force between the table and the block, which we can call force table on block, or also called the normal table on block. So what's a normal force? Normal means perpendicular, and happens when there is contact. If there is no contact, there is no normal force, period. And when there is contact, then there's going to be a force that is perpendicular, and we call it the normal. So what else is interacting with the box? Nothing. That's it. What about the table? Let's do the free body diagram of the table now. Well, the table is going to feel its own weight. Let's put this as red. It's going to feel the weight, mass of the table times gravity. Who else interacts with the table? Well, the block on top, right? The table feels the block, and the block pushes down on the table with a force that is block on table, which is basically the normal block table. Okay, normal block table, ugly B. But what else is touching the table? Well, the ground underneath is touching the table as well. And the ground is pushing up on the table with a force ground table, which is actually a normal ground table because it's touching. Let's do the free body diagram of the ground now. The ground, what does the ground, or the earth actually, what will the earth feel? Well, remember how the earth is pulling on the block down through gravity? Well, the block is also going to pull the earth up through gravity. If this was actually the force of gravity, Earth's block, then we're going to have a reaction block Earth, which is also mg. It's the weight of the block. Notice that it's going up, the other one was going down. This blue force that I'm drawing on the free body diagram of the Earth is the actual reaction to this blue force here. The normal is not the reaction. How do I know? They might be equal because there's equilibrium here, but you can never draw the action-reaction pair of forces on the same body, because the action-reaction, the true action-reaction pair of forces act on different objects. So what other force is acting on the Earth? Well, of course, the weight or the force that the table exerts on Earth, which is going to be mtg. Remember that this was the force that the Earth exerted on the table. So once again, this is the action, that's the reaction. And there is one other force that is also acting on the Earth, which is the reaction to this one, which is the force that the table exerts on the ground, which is the normal ground T. There you go. As you notice, this green force has its reaction on the table. This green action, green reaction. The blue action, force Earth on block. Blue reaction, force. This was Earth on block, block on Earth. Red action, Earth on table. Red reaction, table on Earth. Notice that the Earth is not in direct contact with the block, which is why there is no normal force between the ground and the block. So one of the fundamental skills that we have to develop right now is the skill of drawing free body diagrams, in which you have to include all the forces, contact or field forces, doesn't matter, could be short range, long range, that act on the body. In the free body diagram, we never include the forces that the body exerts on the universe. One last thing, if I were to add all the forces here, action, reactions, and gravities, and normals, and whatever, this will be a mess, right? Because if you consider the block table Earth as one object, then all these forces are internal, and we simply don't write them in the free body diagram, right? So instead, you have to isolate each one of these blocks like we did, each one of these bodies as we did before. Yes, it is true, you could consider that the table with the block is one single body separate from the Earth, and then what you will do is, well, you can combine the weight of these two with the normal and everything, but at the end, what I want to convey is that the interaction between the table and the block will be considered internal and will not appear in the free body diagram. So if we were to do the free body diagram of the system, table, block, we will put the weight table plus block times gravity, and we will put the normal that the ground exerts on the table plus block system, and that's it. That will be the free body diagram of the table plus block system. And we will use this technique later as we progress in our studies of the laws of motion. So a little example, you have a big adult who pushes a little kid. How are the forces? If he pushes with a force adult on kid, then the adult feels the kid on adult force. The forces are the same, but who moves with greater velocity? And the answer will be the kid, because it has less mass. So the acceleration can be big as opposed to the mass of the adult with a small acceleration for the adult. The two forces are identical, right? But the accelerations are not.